Bem, bom dia a todos. É com prazer que eu recebo vocês todos aqui virtualmente para a defesa da tese do aluno Kleber Joshua Sanmartin Atiaga. O Kleber fará inicialmente uma defesa do seu tema de tese, de 1 hora no máximo. Essa defesa será seguida da arguição, primeiro pela professora Elisa Piispa, professora da Universidade de Reykjavik, na Islândia, especialista em paleomagnetismo, particularmente de rochas vulcânicas e paleointensidade, ao longo de vários períodos do passado terrestre. E, em seguida, o professor Wilbur Poletti, da Universidade Federal do Vale do Mucuri, Jequitinhonha. O professor Wilbur é especialista em arqueomagnetismo e paleointensidade. E eu agradeço aos dois, o Wilbur e Elisa, por estarem aqui nessa defesa. É com muito prazer que a gente recebe vocês aqui virtualmente. So just to give the same talk in English, so we are very happy and pleased to have you all here in this virtual room for the defense of Kleber Joshua Sanmartin Atiaga. We have here with us to be the members of the jury of this thesis, Professor Elisa Piispa from the University of Reykjavik in Iceland, and also Professor Wilbur Poletti from the University of the Valleys of Mucuri in Jequitinhonha. I don't know if we say that gets in English. So thank you both for being here with us. Josh, so I give you 1 hour for your talk, and then we get back with the argument of both Elisa and Wilbur.
Yep. Thank you so much for this introduction. Good afternoon, Elisa, Wilbur, Ricardo. For me, it's an honor, really, having you as my my jury. So now I will start my investigation, to present my investigation. Aqui eu falo. Vocês conseguem ver minha tela?
Ainda não, Kleber.
Sim.
Agora sim.
Agora foi.
Kleber, se você puder ocultar essa barra branca.
Tá. Posso.
Muito obrigado. Fique à vontade, Kleber.
Obrigado a você. My investigation is about geomagnetic secular variation for the past 1 million years recorded in lava flows from South Ecuador. So, in this sense, my tutor is Ricardo Ivan Ferreira da Trindade, and also I will present the outline that I will present, or the outline that I will follow. First is the introduction. After that, I have, in the introduction, I will talk about the Earth's magnetic field, the paleosecular variation, and the project. After that, I will talk about the project justification and objectives. Then I will talk about the geological setting, methods, results, conclusions, and finally the reference. So here I will talk about the Earth's magnetic field. So here I have the Earth's magnetic field that is generated at the principal field, generated at the other core. And it happens thanks to the movement of the iron liquid, to the iron liquid metals. So in this sense, we have the iron, and also we have some trace of nickel there. So here, now, as the introduction, I will talk about the paleosecular variation. But firstly, I want to introduce the GAD hypothesis. For the GAD hypothesis, it means GAD hypothesis means GAD geocentrical axial dipole. The geocentrical means the center of the Earth, axial at the middle, like an axial plane, like both sides, and the pole it have two poles. With this hypothesis, with this premise in mind, we can correlation, and we can do this correlation, the correlation between the inclination and the latitude, and that is too important in order to get the paleopoles. So in this sense, the paleosecular variation study, this paleosecular variation studied the deviations that GAD hypothesis have. So in this sense, for this study, I will use these angular dispersions of the all of the virtual geomagnetical poles that as a function of latitude that I calculate for each side on this on Ecuador. As introduced the paleosecular variation, first we need to have here that is the sample that I took, but also the sample locations. But here we need to know, of course, the declination and an inclination, and with this premise in mind, and with this that I calculate from the laboratory, I get the position of the paleopole, and and we need the position of paleopole in order to get all of the virtual geomagnetic poles and the paleosecular variation from these poles, right? So we calculate, as you can see here. Here we have the sample location, and we use a spherical geometry in order to get this the position of paleopole with the declination, as we can see here, and here, and the inclination, as we can see here. But what is the inclination and what is the declination? In this sense, I we know that the inclination is the angle, right, that we have between the surface and the Earth's magnetic field that is generated. But also the declination is the angle between the true north and the magnetic north. So this is important because now I will talk about the declination and inclination a lot. So in order to introduce all of my work, first I need to talk about the thermoremnant magnetization. As my work lies with lava flows, I need to introduce how these lava flows acquire a thermoremnant magnetization. So when the lavas, as we can see here, when the lavas are hot, it all of the magnetic moments are randomly because of the Curie here, because of the Curie temperature is above of this lava flow. But as a measure that it cools, as we can see here, when the lava cools and they go through the Curie temperature, all of the magnetic moments are aligned to the field that at that time to to the field at the time that the lava flow cools. So now I will talk about the project justification and the objectives. In other words, why this project is important and why I choose this project. So for the objectives and justification, first I want to understand the paleosecular variation models, but on Ecuadorian latitudes, and also try to understand how these paleomagnetic fields, how the paleomagnetic field has been changing in the southern termination of the Ecuadorian arc. Here we have the Ecuadorian arc, and here is my study. So here where is the southern termination of this the Ecuadorian arc. But why? With this data, I can improve a little bit the global database and improve the global models like the model G, the model TK03, and we use modern laboratory techniques, taking, of course, taking account the paleomagnetic and rock magnetic data for the past eruptions on this part of Ecuador. However, it is good to say that all of the lava flows that we sample, they are already dated. So one interesting thing to say also is is that I choose this study because the scales of the data in the southern hemisphere, but especially in the southern hemisphere, nearly Ecuadorian latitudes. So in this way, I will a little bit fill the gap of this paleomagnetic data. Now I will talk about the geological setting. It's important to say the many features, the many features in the many features, the main features in Ecuador, but also is good to say that for this purpose, for this study, for this investigation, I sampled around 23 earthquakes from 9 volcanoes, with a predominance, as you can see here, with a predominance of basaltic andesite to andesite lava flows, composition lava flows. So in this sense, all of all of these samples from north to south, we see like a southward migration of the of the volcanic events. For example, here we have the oldest volcanoes, the oldest lava flows, and here we have the new ones, as you can see here, 62 or kilo years, or here at the very north we have around 800 kilo years. Yeah. Here now I will talk about the methodology. For the methodology, it is important to say that I sampled around 23 outcrops, and these 23 outcrops I use a Pomeroy compass, and also I use a, a drill with a water pump integrated in a drill. So this is I add this because in the case that you in the future you want to do some paleomagnetic studies in Ecuador, so the all of the landscape that I see here are really beautiful. So in the case that you wanna see this landscape, you need to do a project here in Ecuador. Of course, I will help with that. So now I will talk about the methodology. The methodology, or the steps that I follow for this investigation are: firstly, I analyze the magnetic properties of all of the samples, but also I analyze the paleomagnetic. I did paleomagnetic analysis. So in this paleomagnetic analysis, in order to get in it in this in this mag, in this magnetic property and analysis, and specifically in order to get the results from the thermomagnetic experience, ERM, isothermal Riemann magnetization acquisition, or even the hysteresis curves or the Fock diagrams, and even anisotropy, I use a kappa bridge, and also I use a BCM, that is the vibrating sample magnetometer. So in order to get all of these paleomagnetic analysis, like the paleomagnetic measurements, after that I did the magnetic excursion analysis, the principal component analysis, and then I plot all of the virtual geomagnetic poles in the stereographic map in order to compare with other models. To start with that, I use a GR6 dual spinner magnetometer, and using both the thermal demagnetization and the alternate field demagnetization. Now is the good part, the results. So taking account the results, we have the rock magnetic analysis. For the rock magnetic analysis, here we have the thermomagnetic curves. The thermomagnetic curves is a diagram between the temperature against the magnetic susceptibility, where these diagrams, or the heating curves, are represented by these red lines, and also the cooling curves are represented by these blue lines. The first derivative for the heating curves are represented by the dark dash, these black dashed lines, and also TCM means Curie Curie temperature, and also TB means the at around the Bergway transition that I calculate for this. The first derivative associated at the heating curve. So as we can see here, the sample is SB1 that belongs to belongs to Sahuatoa volcano, and S23 that belongs to Cariguairazo volcano. So these two samples here and here one show a Bergwen transition, and this Bergwen transition it's around minus 150, and this happens usually because of the transformation of the magnetite, the transformation of the crystals of the magnetite from monoclinic to cubic symmetry. So firstly, we have this premise in order to say that uh, the principal carrier of magnetization here is magnetite, at least for this in this thing. But also for the Curie temperature, we have the all of these, almost all of the samples from my study show show that the carrier of magnetization is titanium magnetite, as you can see here, but with a variable amount of titanium. So a good thing in order to do future experiments like paleointensity, we have that most of the samples are nearly reversible. Yep. So here we see a hump between 100 degrees to 400 degrees, as you can see here, this hump. In this hump, we can see we can say from this hump that it could happen because of the inversion of magmite, or even in some case a trace of pyrrhotite. However, see the chemical analysis from past studies, I I see that this could be better because of the inversion of magmite, and especially in all of my samples, I see like two behaviors. The first behavior is titanium are the first behavior. In the first behavior, I get that the main carrier of magnetization are is the titanium magnetite, but with poor amount of titanium, as you can see almost all of the samples here. But in the second behavior have as principal carrier of magnetization the titanium magnetite again, but those samples as this one have rich amount of titanium, because also again for the Curie temperature and for the chemical analysis from previous studies. So here we have three samples, and here we have a day plot showing these all of these samples. An interesting thing to say here is that most of the samples fall in the pseudo single domain region, but especially all of these samples are more shifted to the left. So those samples are more single domain than all of these that are clearly pseudo single domain. And I will show you now all of these experiments. So here I have the day plot. In this day plot, in this day plot, I we can see, like for example, this sample that is according with the past results, right? So this is more have a more hysteresis loop, more single domain, and it falls also more shifted to the left. So in general, most of the samples are in the pseudo single domain region. In this pseudo single domain region, we have we can see generally for all of the magnetic properties that Wisla Mulmul 1 volcano have two different behaviors. So for this reason, I separate Wisla Mulmul 1 and Wisla Mulmul 2. In this sense, in general, I get the total of my samples. We have 7 samples more shifted to the left that are more, all of these ones, more single domain, 11 samples in like in the middle that are pseudo single domain, and these 3 samples that you can see here, all of these these 3 samples from here, SE1, SE15, and SE23, that is this one, are more like multi-domain, and it show like more multi-domain hysteresis loop. And of course, we don't need to forget the Chimborazo volcano that are more more contribution, as you can see here, and by this was widespread hysteresis loop, more like acting two components here, and I will show you this also in future results. As you can see here, that also in the fork diagrams, firstly the fork diagrams show the coercivity against the interaction of the interactive force between each coercivity, right? So, and I need to introduce also the isothermal Riemann magnetization, this diagram from here, that generally it explains or show the applying field. We have here an applied field against magnetic remnants. So for this, we can see better how many components this sample have. In this sense, all of these data confirm again the hysteresis data, and especially these SE3 and SE20 show a typical single domain fork distribution. However, sample SE9 and this sample from here show like a hysteresis loop, a pseudo single domain like for distribution. Sorry, no hysteresis loop. And again, now I will talk about the isothermal Riemann magnetization, that in this sense, the majority of the samples are below of 0.3 Tesla, or they saturate below 0.3 Tesla. In this good indicator, because this is like are indicating us a presence of low coercivity mineralogy. Of course, with the exception of the four samples that I said before that have a more multi-domain component. So these four samples could be because of the coercivity. It could be happen because of the the coexistence between a low coercivity mineralogy with a high coercivity mineralogy. So the coexistence of these two samples. Now I will talk about the anisotropy, of magnetic susceptibility. Here we have that the mean magnetic susceptibility. Well, first here we have all of the scalar results of this anisotropy, and the mean magnetic susceptibility is around 0.02. Is like that it means that they are really in the range of this of the andesite lava flows. But also to explain better this, here we have that all of these these values. Here we have the mean susceptibility against the number of samples, right? And also here we have the degree of anisotropy against the shape parameter. Here we have the mean susceptibility against the degree of anisotropy. All of these points are the different volcanoes. And finally, here we have the magnetic foliation, that is a good indicator of the lava flow, of the direction of the lava flow against the degree of anisotropy. It's interesting to say that here we have that more samples present an oblate shape, as you can see here. The majority of the samples, 57%, presents an oblate shape, where just the 43% present an prolate shape. So this is like the shape of the grains from this for the ferromagnetic grains. And also, one interesting thing to say here, we can see a direct relationship between the magnetic foliation and the degree of anisotropy here, as you can see in this part. Now I will talk about like for the anisotropy directions. These yellow arrows, here we have a stereo plot with all of the with all of the measure from the maximum, the minimum, and the intermediate the intermediate axis here. However, these yellow arrows represent the magnetic lineation. So this magnetic lineation in some papers I read that could be parallel to the flow direction. However, normally we need to test this with other results. So in this sense, here normally we have a normal fabric. A normal fabric are when the minimum component are in the middle, as you can see here. But almost all of the samples here we have like a normal magnetic fabric, and fabric is like the predominant fabric, the predominant feature from my stat. And just four samples, as you can see, the SD7 show an inverse fabric. And in January, you can see here all of the patterns. We can see like any pattern taking account the magnetic lineation. However, this and with the magnetic foliation is better in order to say a little bit more about the flow direction. So here we have the anisotropy direction. In the anisotropy, for the anisotropy direction, also we need to study the magnetic foliation, which this is for sure in some papers I read that this is for sure is parallel to the flow plane, and could be parallel to the flow plane. We need to say also, we need to see before if this is have a normal or intermediate or minimum fabric, and normal or reverse fabric, sorry. In this sense, we can see, for example, here the Wisla volcano, that is this volcano from here. Let me, yep. Here, as you can see, the Wisla volcano. This Wisla volcano shows like a clockwise magnetic rotation, taking account the magnetic foliation. So in this, we can see that this Wisla volcano starts from nearly vertical magnetic foliation here, and it moves like in clockwise rotation. This is a good indicator until we can see like more for SZ11 almost horizontal magnetic foliation. So this could help us to say that this volcano, all of these lava flows were the as you can see here, all of these lava flows from Wisla volcano is interpreted as multiple lava flows which were fed by the unique crater. And again, after that, all of these lava flows were deposited successively. And also with, as I have all of the dates, I can corroborate these results. And finally, one interesting to say here with anisotropy is good to see here the high dispersion of SZ14. In this sense, even the proximity of the source band, it is dispersed, and it could be because of the thermal effect of the crater, but also it could be because of the morphotectonic movements from the Payaptanga fault that I will talk about later. Now I will talk about the paleomagnetics. Here, the paleomagnetics, yeah. First, for the paleomagnetics, we can see these Seiderberg projections that are those diagrams for here, and the model plot for this study. In generally, we have from these paleomagnetic results that more than 95% of the samples demagnetized before 100 millitesla, and the other 5% demagnetized at around 120 millitesla. So it is a good indicator again that possibly the main carrier magnetization is the magnetite. And of course, using thermal demagnetization, more than 80% of the sample lost the thermoremnant magnetization at around 180. Again, as we can see for the thermomagnetic curves. And again, for this with these results, we can corroborate again that possibly the main carrier of magnetization are titanium magnetite, where with variable amount of titanium, but generally poor amount with poor amount of titanium. And in some case, in really few samples, we see here like the inflection, this inflection from here, that it could be the presence of magnemite, but also here that this sample even at 600 degrees, they didn't reach zero. So here we have also the presence of hematite. A little bit in trace pass, right? So now I will talk about again the paleomagnetic results, but in this sense I will have the statistics from here. In general, we have that the mean direction for all sides of taking, and I use the Bantam cutoff in order to get better and accurate results. So I took two samples, and I will explain later. And even I took off those samples because they give us a virtual geomagnetic pole dispersion really high, and they possibly are in the same range of two of two of this of two magnetic excursions. So in this sense, we have that all results are really near from the geocentric axial dipole hypothesis, and that means that at least we are close to the models, and it will help to improve the models. But also, my results are consistent with early data published by of Dyke. We can see just a difference, a really close difference of few degrees. And also the one interesting thing that I take this and corroborate with past studies, we have even a close mean paleopole than other studies, that we have a paleo latitude at around 85% and a paleo longitude at around 200 degrees. With again, I apply the banda cutoff in order to get all of these all of the paleo poles, all of these virtual geomagnetic poles. So now I will talk about the paleosecular variation. Here, the paleosecular variation, as I explained better, I I have a virtual geomagnetic pole dispersion, that is the means of the paleosecular variation of 15.6 degrees. In this in this part, as I said before, I exclude the two sides because of the because of the band and cutoff, but also because of the magnetic excursions that I will explain in a few moments. And the good thing here is that even these virtual geomagnetic dispersions here is really close from the past study in the continental Ecuador. That is this study from here. So this is just of 1 degree of difference from of Dike study, and is like more difference here. But also here the difference could be because this study was uh, was made on Galapagos Island. So in Galapagos Island there are no too much tectonics as happens here in the Ecuadorian Andes, and that is one of the reasons why we have the two studies here in continental Ecuador and at around almost the same value, at around 14-15 degrees, taking account this the virtual geomagnetic pole dispersions. Now I will talk about the magnetic excursions, and I talk about this because as I have the data from these samples, we see here that SE21 and this sample from here, SE03, are or fall in the same range of the orphan cornell excursion in this and the monoleg excursion. And also, these two excursions and these two sites give us a weird paleopole. So for this reason, I will see the magnetic excursions, and we see that those excursions and those lava flows uh, possibly were deposited in at the time of these excursions. And I found another papers like Thoubeni et al. that it that it that he see something weird in Galapagos Island, that is Ecuador too. So here in the Galapagos Island, at the same age of the orphan cornell excursions and at the same age of SE03, so we could correlate all of this in order to say that, of course, that yes, here SE20 SE03 probably was deposit in this in this excursion, and also help here that they also see something weird taking account these the magnetic excursions in Galapagos. And now I will talk about a little bit about the tectonic implications. And I see again some weird paleopole from SD14. So I was thinking, look, what is going on for this sample, right? And I found a really nice study about the morphotectonic movements of the all this the Payatanga fault. That this is the one of the main faults here in Ecuador, and as this fault could this volcano for sure it affects all of these lava flows, and it affects all of how these lava flows were deposited, and these morphotectonic movements could directly the SE14. So it gives us these megas to think that possibly some tectonic deformation happens here in SE14. And of course, taking account this deformation and taking account the aware paramagnetic pole, we can conclude that, of course, in less proportion, but this this Payatanga fault affect a little bit even the fabric, but even the how these lava flows were deposited. And some of the conclusions that I will tell, at least that the main conclusions for me, we have again the main chiromagnetization that for almost all of the samples are titanomagnetites, but with different amount of titanium, but generally with poor amount of titanium. Just the calpi and lictocones, they are titanomagnetite. The main chiromagnetization of those samples are titanium magnetites, but rich in titanium. And of course, the principal the and all of these samples fall in the pseudo single domain region, and 7 samples a little bit shifted to the left. Those samples will be the better one in order to do, for example, future works like paleointensity. Another conclusion that we can see here are the principal that the principal source of the inverse fabric could be by the presence of these of the single domain magnetar. But in our case, those samples are most of the samples are just in the middle. However, one sample is a little bit shifted to the left, but even in the pseudo single domain region. The mean duration is a good indicator because the mean duration is really close from past studies and really close for the GAD hypothesis, and really close also for the study for in here in the continental Ecuador and in the insular Ecuador. And the mean paleopole direction also is a good result because these results without these two samples that of course those samples were was in the limit of these two excursions are are also consistent with the early data. And from all of the 23 sites, we see that 21 sites are in the normal polarity and two sites are in the reverse polarity. But again, these two samples from this normal polarity are like giving those two samples giving give me like really really weird polypole. And these weird polypole are because they fit perfectly here in the orphan canal and in the monoleg excursion. As I can say before, the Victor geomagnetic dispersion, that is the paleosecular variation here, is really close than previous studies. And finally, the paleosecular variation from one study is a little bit lower, too much lower, right, than the Updike study, because of this of that study was made in the Galapagos Island. So there is not too much of tectonic activity. And finally, this high tectonic activity, as you can see before, for the morphotectonic movements from the Payotanga fault or something like that, we have this main feature could affect a little bit the anisotropy, and also we get an inconsistent Britten geomagnetic pole. So here are the reference that I use for this presentation, and of course I want to acknowledgement give I want to eu posso falar, acho que no português agora. Eu quero primeiro agradecer para muito para Ricardo, que às vezes eu acho que eu escrevia muito para ele. Mas I also want to say thank you to Elisa, that it was the teacher who helped me at the beginning too much in order to get all of the analysis, in order to guide me in order to get this investigation. And of course, for Ricardo, that he was in Sao Paulo, my teacher, but also my friend, because many problems that I have there in Brazil. So there is like my first acknowledgement for my two teachers, and of course for my parents, that always they are here for me. So thank you so much. I hope the presentation was clear. And if you have questions, please let me know. The questions, of course, you can say it in English and in Portuguese. And yep.
Thank you, Kleber. Thanks a lot. Congrats for the presentation. So now we pass to the second part of the defense. Kleber, would you like to have some minutes for drinking some water, or if you want to have, we usually give you 1 or 2 minutes, then we start.
Please.
Okay, go ahead. No problem.
Thank you so much.
So then in the next step of the defense, we are going to have the two members of the jury starting with the arguation questions. So I would like to call Elisa Piispa, Professor Piispa from the University of Reykjavik in Iceland, which was a collaborator, and is just like Kleber said, was his teacher in Ecuador and responsible with him for the most of the sampling. I'm very happy to have you here, Elisa. It's unfortunate that you are not in Brazil. It would be much more reason to have you around, but it's a pleasure that you accepted to be part of the jury. Then you have now 1 hour of questions that you can make the questions, and Kleber can answer by his turn. If you want, you can also make all your questions in a block, and then he answers in a block. So you decide what's the best way of doing it. Okay, please, Elisa, thank you very much.
Okay, thank you, Ricardo, and thank you, Joshua, for the presentation. I guess I have some pre-prepared questions and some also now from the presentation. I guess I'll start with the ones I had pre-prepared. Let's go here. So could you elaborate a little bit on the significance of studying paleosecular variation in the southern hemisphere, and particularly in the southern Ecuador, and how does this contribute to our understanding of Earth's magnetic field behavior?
Yep, sure. Thank you so much for these questions. Please let me show you right in the presentation that is, I can show you better how this could improve these paleosecular variation models. Let's see. Yeah. Yeah. So, first, we have nearly at the equatorial latitudes. So we have, as we can see here, just a few studies. But also, I took one study from this part that is nearly equatorial, the equatorial line, but also are in the southern hemisphere. As I said before, these the 2/3 of all of this kind of study, all of the paleosecular variation study are in the northern hemisphere, right? Like in Mexico, in United States. So because those have the laboratory, and it is really good. Like for example, get more studies, more paleosecular variation studies, more paleomagnetic studies, like in Africa, that we don't have many studies. We don't have a lot of this kind of studies. So this is important. But also it's important because when you was here, I think you was the one of the first that want to introduce the paleomagnetism here. So also in Ecuador, as we know, all of the paleomagnetic analysis, the paleomagnetic measurements are really difficult, right? Because here in Ecuador there are not this kind of instruments that I use in Sao Paulo. So that's why it's important here near equatorial latitudes, but also why this is important in the southern hemisphere, but again also in Ecuador. That in Ecuador there are just a few studies, and the paleosecular variation models here give us a little bit to understand and to improve like all of these. Let's see, improve like in order to get better algorithms, because this model G and model TK03, those two models are a little bit old, and of course a teacher from Sao Paulo, Daniele Brand, she create new models, new paleosecular variation models. And of course, if you have more data, so you will have more precise results. And the good thing is that all of our data that we collect are dated. So now, even that we have the data, we have the date of this data, so we can we can mix both, and we can have a better models. So I think I answered the question, but if you have more questions, just let me know.
Yeah, I guess could you still maybe what in your figure with the data around the globe, what kind of data is that?
Yeah,
What
here
kind of study? in the not this one, the figure with the on 2/3 of the data.
It's below. Yeah.
Yeah,
This one.
yeah.
And then the second, then can you also then maybe explain a little bit more about the models, the G model and model G, and those, the TK03, the differences or similarities, a little bit more about those as well.
Of course. Yeah. Here first I will explain a little bit of this of this data. So this data, this study focus on the paleosecular variation studies, and that is why I took this this map, because in this study, making statistics, we see that are just the 33% of all of this data was created, was made on the southern hemisphere. So this is more like the paleosecular variation models. So for also for these two models, they all of these two models, the model TK03, I remember that this model used the spheric harmonics formulas in order to get all of these deviation from the gut. But also this model study those spheric harmonic those no dipolar components in order to get this model. And also the model G, that is the last model. Let's see. The model G, that is the last model. Honestly, I remember that I just took that formula and I add my data for that code. But also that model try to that model get some studies from the past, and with that model take some studies from the past, and with some and really that model I will try to see now that I did before.
Josh, you presented the basis of the model G at the beginning of your presentation.
Yeah. I'm so sorry. I think the nervous. So this, yeah, I remember now. So sorry. Here we have the model G, and where this the model G that this is that here we can hear we get this the virtual geomagnetic pole dispersion, of course, as a function of latitude, but with these with the symmetric and anti-symmetric components. So in this sense, we have we use like this least square approximation, and also we use these symmetric and anti-symmetric parameters, right? That we that we have in here in this geodynamo parameters. I'm so sorry. I think the nervous.
No worries. Okay, thank you. Let me move on to the next set of questions. So I guess here, what were the main challenges you encountered during your measurement, data processing, and analysis, and how did you sort of overcome these any challenges that you had? More like a general question.
Yeah, no, I think more than the challenging for all of the measurements was the challenging to study in Brazil, but also for the challenging for the measurements that that I that I remember in some case to process the data, because I need to read a lot in order to get the paleosecular variation, because I read like 4 papers, those 4 basic papers about paleosecular variation, and I didn't understand. I think after 3 months that I studied that, I I said, no, I think that is this paleo dispersion, because I when I read the first papers, I read just formula, and I get I don't I don't. But after that, I was like trying to touch these first, to do all of these, to get all of the paleopods, that it was not really heavy, but to process all of these paleopods in order to get the paleosecular variation. And also I get the no dipolar components, but I didn't add because I was not sure. So these data, the paleosecular variation, and do the statistics from that, also was really heavy. And also the fork diagrams, because in the past I didn't I I I know I didn't use the fork diagrams. So first I need to read why we have this beautiful image, and why for example this diagram is like pseudo single domain, or why this diagram is single domain. So I need to understand behind the diagram, not just see this diagram is pseudo single domain because you see here. No, because so I was trying to understand each curve, and then and after that each curve do the inversion in order to get all of the all of these the fork diagram. So I think the fork diagrams and calculate the paleosecular variation, it was the main challenges. Of course, after that I get all of the paleos all of because firstly I did the paleosecular variation from all the sites, and then I see that the Van Damme cutoff just moved that, and I didn't understand that also. So I was reading what is cutoff, what is the Van Damme cutoff, what kind of cutoffs I can use. If I use a better cutoff, what is going on if I use another cutoff. And I use that cutoff because that's the cutoff that most of the papers use. So in this sense, in order to after that I get all of these paleopods, so I'm trying to correlate what is going on with the weight Britten geomagnetic pulse. So after that, I see all of these virtual geomagnetic poles and try to correlate all of these virtual geomagnetic poles with all of the geology that happened in Ecuador. So that is a challenge, right? Because I need to read a lot about Ecuador, about the geology, about what is going on here, if there is more complex studies or there is more studies, and that is why I find it too many paper in which they didn't talk about the Galapagos anomaly. They just add that figure and they didn't say nothing. So I was trying to see all of the figures that I can, all of the paper, try to read all of the papers that I can about excursions, and I see just like a point that said Galapagos. So I said, why? And I tried to find Galapagos in the paper, and I didn't find. So that the scarce data on Ecuador also, I think, is a challenger to study in order to get nice results. Because in Ecuador, they are here in Ecuador, it produced investigation, but no investigation as in Brazil, as in Europe. That the investigation in geology, in many things, we have more data to compare those those models.
Okay. Actually, then you mentioned the Van Damme cutoff. Is it the same cutoff that Opdike and Kent used? And then like another question is related to that: how sort of confident you are that your your dispersion is real, what are your caveats? Like what are the problems, potential problems, and reasons that it might not be true dispersion, or it could be true dispersion? So like elaborate more on that, please.
Yeah. Of course, the things that I remember, the band of cutoff, yeah, it was used in. I think I am pretty sure that it was used at least for the G model, but also in past papers, in past investigations that I take as reference for my investigations, the first cutoff that was used uh, was the Bandam cutoff, and I was reading this Bandam cutoff that even is, I think the Bandam cutoff it is from 1994, if I remember well. So it's a little bit old, and now, of course, there are the scientists are creating more cutoffs in order to get accurate results. However, even this cutoff is old. This cutoff is one, or if not one, is the more al menos from all of the papers that I read, in 99% of the papers they use this cutoff. That is why in order to get the another publications that I read, and also in order to get the publication that I used to do my investigations, so that is why I took the Van Damme code.
And
And
did Kent and Opdyke use it in their data sets?
yeah, Updike for sure they use the Van Damme code. Kent, honestly, I don't remember, but of course, but I think I'm pretty sure that that is the 99% that I said before, because almost all of the papers that I read, that from all of the papers that I add here, that are in to do the model of the paleosecular variation model, I remember that most of the almost all of the publication use the Van Damme cut.
Okay, and then the second part of the question was like how confident are you that you are capturing dispersion signature and it's not something else that you're viewing?
I am really confident because as let me share the science, we can say something now, but in January here, I was uh, after I took off these two great paleomagnetic poles, I was really confident. I was happy, right? So because I get, for example, here, this paleosecular variation model, my data is really close to the data from Updike, and Updike, they uh, Updike in Updike, they study a lot more samples than my study that I just took like 256 samples, something like that. And Updike, they use like 900 samples, and that's because the logistic is the logistic that I could study. But here also these Updike samples, as you can see, there are just a few degrees, 1 degree, less than 1 degree in comparison with this study. But also this is really close to the model G, and also a little bit no, not really close from this the model TK03. But if we can see all of the data, no, not these data are exact in the model. All of these publications, even with in 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 latitudes at around 50 or 70, we can see even. Oh, sorry. Yeah, with this, we can see even those samples are really are not really, they are not close to the models. And also, so here we get these samples in Ecuadorian latitudes. As I said before, that there are no many studies are really close to this. And also, this is good because I just took all of these samples I just compiled all of the samples from 1 million year. I did a compilation from the 1 million year compilation. And from this 1 million year compilation, and after that I add these two samples that have more than this this range. So all of these samples and these two samples and also these two models are in the error parameter in the error of my data. So that is why and also I use these modern and new techniques and I use all of the instruments for the Sao Paulo laboratory, that of course there are too many publications using that instrument, and also my data with a good correlation with the X give me make me to think that these results it could be really close to that model. And also, as you can see here, these paleo poles are just that too, because I just try to find why those two samples have like inconsistent paleopole, like no don't show like a paleopole consistent with the models. So I just take these two samples, and after that, even that these samples falls in these two excursions. And again, as I have all of the data and as I have all of the dates of these samples, I see that as here in this table that I add just in case. So just these two samples are in the inverse polarity, and of course just that two samples I was like crossing my fingers in order to see, oh, I not. So yeah, just these two samples falls in the reverse polarity, and these 21 samples, as I have all of the data, all of these samples with this data that are in a normal polarity, again these samples again fall here in the normal polarity. So I because of the modern techniques and all of these data is really close even to the GAD model, right? To the geocentric axial dipole model is not really really far from the model. So and really close to the other studies. I think that these samples could be, of course, good even for a publication.
Okay, thank you. Let's move further. How much time do I have? I still have plenty, right? Yes, I do. You mentioned in the thesis itself, not in the talk, you mentioned something about these that there's let me see here again. I have it here, this question. That's the VGP distribution being sort of higher in continental Ecuador, and you said that it could be a strong longitudinal variability associated with non-dipolar components of the field, which then can be associated with the South Atlantic magnetic anomaly. Could you elaborate on this finding, or that was one of your, I guess in your abstract, it was one of your conclusions?
Yeah, no, thanks for the questions. Yep. So here, can you repeat the last part of the question?
So can you just elaborate more on the possibility that you've hinted in your abstract of the thesis about this sort of high VGP distribution being due to the South Atlantic magnetic anomaly. And I guess you can maybe explain the term, what is the South Atlantic magnetic anomaly as well?
Yeah, of course. We have the South Atlantic magnetic anomaly that they are now in the, of course, just at the point of Brazil, and even it touched like a little bit. Can I show you like a figure of that, or there is no? Yeah, let's see here. South Atlantic magnetic anomaly here. So let's see, in order to the audience also to have a. So here we have the Southern Atlantic magnetic anomaly, and you can see here even this this magnetic anomaly just passed, but it passed like is the all of this, the influence of this magnetic anomaly is low here in Ecuador, but also it could be affect these magnetic anomalies in order to get great results in especially here in Brazil, but also in Ecuador, because also it passed here, and some of these samples, some of the samples that I study, they are not old. For example, I have a sample from uh, four 4 kilo years. That again, that sample that of 4 kilo years even could be affected by this anomaly, and it could be like a little bit changed, a little bit, for example, the declination of inclination of the paleomagnetic results here. But again, it could be like affect directly from some of my samples, because we know because I know the date, but also these samples could be affected, but in minimum proportions, because of this because of this the South Atlantic magnetic anomaly. That again, in Ecuador, unfortunately, is not this magnetic anomaly is not like is continually affecting us in this part, that even some satellites could, I heard that even here some satellites like they just didn't work when they passing over there, over that anomaly.
So this anomaly was not there in the past?
Yeah, it was. It have like a migration, but even with the migration, it took also. I think most of my samples, because they are I think here just a few degrees in the past, very past from my oldest sample. But it affects, but of course, as you can see here, it could affect in less proportion, and that is why, and even that could be the reason why we have like this dispersion, that we had different results from the models, because of the magnetic anomaly, but also because of the different tectonic features on Ecuador.
Okay. And then can that then explain the difference between the VGP dispersion in continental Ecuador and then in Galapagos?
Yep.
What is your sort of main reason for that? I think you did mention that in the talk, your thoughts on that. But yeah, again, maybe discuss a little bit more about that.
Oh yeah, thank you so much for the question. Yeah. So as we can see in this map, Ecuador is like a really nice country in order to feel the earthquakes, to feel the volcanic eruptions. So that is why that happens, because of the Nazca plate is subducting against beneath the South American plate. So because of this subduction at this decarnate ridge, that is a oceanic ridge, that even that is more like our, it's more like the pressure here is more, and also this the Grijalva fracture zone that have this fracture zone that belongs to the Oceanic Pacific, goes through this go through Guayaquil. So here, and it passed directly from my volcanoes. So all of these features, even that is why we have a lot of volcanoes, all of these Western Cordillera, the Interandean Valley, and the Eastern Cordillera, as here is not really clear. But for example, here you can see all of these blue, green, yellow, orange, orange things are volcanoes, and those belongs, for example, those volcanoes. Here is my study, and you can see here as this Grijalva zone are just cutting some of my volcanoes, some of the volcanoes that I study. But also in Ecuador we can see many volcanoes. So these tectonics and these magmatites, of course, will change a little bit. It will change a little bit even for the tectonics. It will rotate, it will tilt some of my lava flows. And in this sense, it's essential to say that there is not just the tectonics, right? But also it could be for the other effects like the South Atlantic magnetic anomaly, or also the other effects like the magnetic excursions, as I said before. But if someday one people that is seeing this in YouTube, is or some of the jury want to come to Ecuador, it will be really nice, because you, at any part that you see from on Ecuador, you will see, let's see, you will see volcanoes, and that tectonics, that magmatism, of course, at some point will affect, will erosion. For example, that volcano, and that because of the this subducting zone is still active, so it will create new volcanoes. It will recreate more fracture zones and something like that. And for example, in some day you want to come to Ecuador, that is why we have a lot of volcanoes here, and people who wants to study volcanoes here, and of course Islandia, that is better, will can come to study volcano. For example, here I remember that this is SZ14. Uh, 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 uh. Just 1 minute. Here I remember that we like almost killed the Elisa's car, but finally we arrived here. But after that, and that we walk a lot, we we can see really, really awesome landscape, really awesome volcanoes. And now I don't know what is going on. I think something happened with my PowerPoint. But this video is awesome. And in some day you want to come to Ecuador, of course you will see. Yeah, now you will see all of these volcanoes. Even now there are two volcanoes here in Quito, well, one volcano here in Quito that is active, and some days they erupt like ash or something like that. It's awesome. So just let me show you. But the people learn to live with that, right? It's like just that. But for example, for the people from United States, they are like 20 videos, 20 photos from that. But for the people here, it's like, yeah, all days happen that. So for example, here, and let's see, here we can see a volcano. Here, look this. So all of these are volcanoes, but here we can see a volcano with snow. So that is the good thing from Ecuador. I think that is the Altar volcano. So all of the mountains that you see, you will see volcanoes. You will see that this this part of Ecuador is even in construction. So of course we have here many tectonic deformations.
Okay, I guess then related to that, what's the sense of motion in the Payatanga fault?
The sense of motion, as I said here, it has like here um is strike slip motion. So here we can,
Is there no vertical component at all? Is it just strike slip?
yeah. So here let's yeah. So here, no, this is yeah. So here we have this Grijalva song where this sample, this part, this block, not this sample, sorry, this block go towards to this way, and this block go towards to that way. So that is the sense of this this like transformer fault, and that is why we have this feature here, right? In Guayaquil, we have the Gulf of Guayaquil that is made because of this huge Grijalva fracture zone. And again, this is important because it could two of my volcanoes, two of my volcanoes.
And so if it's a strike slip fault, like just lateral movement, how it would affect on your directions then?
Yeah, it's not that is the moving, right? The movement, right? Like strike slip. But of course, when at the moment that it is create that this fault is moving, of course it will it will all of this part of the cordillera, all of this the western cordillera, the eastern cordillera, and in the interandean valley, we have successive movements associated with this fault, because when this fault moves, it could activate the other faults, and it could activate even this. For example, here that I found this publication, it of course will affect this, that are the more morphotectonic movements here, for example, here in the Igualata volcano. And of course, that movement, at the same that it moves, it will create more fractures. And for example, in the volcanoes, that even here we can see this, that this is the fault. So we can see even in a big scale how this affect the landscape, and even could affect, of course, or
But on your sort of paleo direction, what would it do? Like for example, is it SE14, or which one was the one that was affected?
yeah, SE14.
Yeah. How does the direction from that look like on your stereo plot, for example? Which one is it?
Let's see. Yeah, the three samples that, for example, here, in order to see the paleo poles, the SE14 is this one, if I remember well, because all of these, yeah, is this one. So these samples are still inside of the band and cutoff, but of course it could it could be affected by this Payatanga fault. So that is why I use this as indicator in order to get in order to trying to explain why this sample and the declination or inclination could be like not the same, because this block could be tilted a little bit, but it tilt not too much, but of course it tilt, because also I was trying to find from each data that I have what happens at any what happens at that time on Ecuador, and but I didn't find anything from these samples. I just found for SE14, SE SE3, and SE21.
Yeah. Kleber, just sorry for introducing Elisa. Elisa is trying to say is that if it's right slip only, it will only rotate the direction. So the only change you would expect to have is on declination, not on inclination. That's the main point, I think.
Yeah.
Now I understand.
Okay, we'll move on. Do you have an example where you would have done the alternating field demagnetization and thermal demagnetization on the same site? And how well did they correspond, or did they not correspond, the directions?
Yeah,
either from same sample or same site. Do you have available here?
Yeah, let me. This is not my computer, but I think at some point. Because I have here all of my data. So when I did the thermal demagnetization, here I have all of the data, and I did the the thermal demagnetization and the alternating field demagnetization. All of these samples all of these samples were like like, for example, if I have a sample of, let's see, for example, if I have a sample that in here that we have a thermal demagnetization, it falls, for example, until 500. We have a Curie temperature at around 580. Also, for the alternating field demagnetization, these samples also these samples also lost their lost their natural Riemann magnetization at around, for example, 80 millitesla or something like that. So, for example, this sample that we have SD22, this sample also in the thermal, but I will show you. Let me see. But this sample also lost their natural Riemann magnetization using the thermal demagnetization. The thermal demagnetization at around 6. For example, here it lose at around 6. It lose all of the natural Riemann magnetization at around 600, 610, 620, something like that. But for the thermal demagnetization, this sample also, if I remember well, for example, for this sample also, as is the thermal demagnetization, this sample lose all of the natural Riemann magnetization at around 620. But for the alternating field demagnetization, it lose all of the magnetization at around 110, 120. So those samples are using thermal and alternating field demagnetization in all of the case are consistent.
But so like the direction itself, like the directional data, like
the direction
they look similar.
Even the direction and even where they lose all of the natural Riemann magnetization. But let's see if I have, because I have the data, but I don't remember, because this is not my computer, if I have the Remasoft, because I have the Anisoft.
Also this is something that could be, it would be just nice maybe to see in the thesis to sort of like an example with both methods right next to each other. Just maybe we don't have to go much deeper in it. I'll trust your word that they are similar for now.
Yeah, of course. You will get the access to all of the data.
Okay. Let's see. That I already asked. I guess also that a little bit more bit broader question again in between. So how would you improve this study, or sort of if you would have chance to do future work within this project, what would you do to improve this?
Yeah, in order to improve this model, I could use now I have all of my data, but I can use all of the past data to that all of the past data on Ecuador, that there are like some really old papers that even they are not in the tables, and I could compilate all of the data that I can find, and I could calculate for myself the virtual I can calculate the paleopoles from that, because they are just show like paleo just declination and inclination, standard deviation, something like that, but they didn't show like the paleopoles or the various or paleosecular variation. So first I can compilate all of the passwords from Ecuador, that there is not too much, but there are some papers that are really uh, really at the very end of the Google. So I can first do it that, and after that I for sure the next step that I want to do for the samples is paleointensity, because with paleointensity even we could corroborate the my data, the age of that data, even with the excursion of that, and even with the intensity that in general in the models it must to be in Ecuador at those ages. So the main thing that I want to do I want to do for improve this investigation is paleointensity, and that is why I are in all of the presentation I am trying to emphasize in which sample are single domain, because generally those single domain are better for paleointensity studies. Of course, we can get also sample. We can took also samples for in the that fall in the that fall in the pseudo single domain region, but the most accurate samples could be those from the single domain, and those samples that are nearly reversible in the thermomagnetic behavior, right? Because with that we can improve not just the paleosecular variation model. If not, if I could improve also, yeah, now the three components we have the declination, the inclination, we have all of the data, but now we have a three component that will be in this case this the paleo intensity, the paleo intensity in this zone. That honestly paleo intensity there are mm, less studies than paleosecular variation.
Okay, thank you. Let me see. I think I'm getting close to having most of the questions that I had prepared. Yeah, you already talked about the cutoff. I guess, yeah, maybe that's could be my one last. So you already mentioned that you experimented with other cutoff values. So which ones and what did you do?
Yeah, I I was using I was did first of course the banda cutoff, because that was the main cutoff that, as I explained before, was used. But also I applied a cutoff because I was trying to figure out how the code works, and I was applying different my own cutoffs, if I said if I could say if I could say that, because for example I was applying cutoff just at the middle. I was trying to apply cutoff just at 45 degrees, for example. The cutoffs at 50 degrees. in order to get how this data moves, or how this data, for example, could have 10 degrees or something like that. I was just playing with the degrees in order to see what is the difference between the Van Damme cutoff and the other cutoff. And the cutoff, and just change the angle between the 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 angle be from each the angle from each latitude.
And how did it change your VGP dispersion estimates then?
Yeah, as as first I took like a cutoff or 5 degrees, so it changed a lot because they are just give me the true sample, right? Then I was like moving in order just to see what is going on with the data. But even with 14 samples, they looks with 14 samples. I remember that it was a cutoff uh, really low degree. Those samples are almost the same data. So when I applied a cutoff of 40 on 40 or something like that, it was almost the same data. But also when I applied a cutoff of 5 degrees, so the data changed a little bit, and this with this we are close to the model, but not close to the past studies.
Okay. I guess, yeah. Thank you, Joshua. I think, yeah, I'm happy. I'm exhausted my list of questions pretty much. So thank you.
Thank you very much, Elisa, for this comprehensive review of the thesis and the IGUation. Thanks a lot. And then we get back at the end of the thesis just to do the whole assessment. Now I would like to pass on to Wilbur Poletti. Dr. Wilbur Poletti is a professor in the University of, now I will say it right because I changed the name of the University of Wilbur at the beginning. It's the Federal University of the Valley of Jequitinhonha and Mucuri rivers. So thank you very much for being here. And Wilbur, you can choose, like you can do your arguation in Portuguese or in English, or like mix between both. I think that Kleber is going to understand everything.
Okay, thanks, Ricardo. I will try to speak in English to Elisa, follow us. But if I fail, just let me know and I change to Portuguese and let's discuss your work, right? First of all, I would like to thank you for invitation to participate in this evaluation. Thank you, Ricardo, Kleber, and nice to meet you. And I would like to start by sharing a little bit of my overview of your work, okay? Make some comments. And then I will ask you some questions. So you analyzed a large number of samples from 23 sites collected from volcanic complex in Equator,
In Ecuador.
which is, sorry?
No, just
Equador, which is a region that has little data. Also your results are over the last 1 million years, which means the period and the location are super relevant in my view. You performed a great set of magnetic mineralogy, AMS, and polydirectional measurements, resulting in a set of high quality estimation. So I think it's super important. Regarding the dissertation, the structure and writing are very good. I'm not native, you can see English native. I just try here. So I encourage you to ask some colleague to make a detailed read You understand me? But I think the right is very good. As well, the presentation of the results. So congrats about that. But in relation to the discussion of the work, you addressed several research fronts, I mean, area of knowledge. For example, you talk about AMS, paleosecular variation, excursion, tectonism, but I really didn't feel that you went in deep with any of them. That's my impression, but it's important to highlight that you included them in an interesting way. So specifically, the interpretation of AMS with the structural geology was very well explored, but from I understand, there was no new conclusion. That was my understanding. So to conclude my general comment, I would like to congratulate you on your interesting work, mainly about the number of rules data. I think it's really important. And I'm sure that the volume of the measurement and analyze is very important and will be used in future work. So now I would like to ask some general question. Elisa made one, the first one about the difficulties, and you give the answer. And now, in addition to what was presented in your dissertation, did you work on other sub-projects? I mean, you did different measurements, you try different methodologies, or all your results is in your dissertation?
Yep. So at the beginning, I was trying all of the things. I was trying all of the things. I want to use all of the Paleomag laboratory. Honestly, at the beginning when I arrived to Sao Paulo, because when I see the laboratory, I said, "Wow, it's like other world," something like that. So I was just walking and the door open, something like that. So when I arrived to Sao Paulo, I want to do many things for my samples. And I said, of course, I will do paleomag, and I want to do paleo intensity, and I want to do my own model. So of course, from my data and starting from my data, as I know a little bit of programming. I don't remember how to say it. So I was trying to do like a model, and at the beginning I was talking with Daniele that she published a paper related with the models. So at the beginning, I even with my few data and with the data on Ecuador, I want to do like that things or thinkings or baby investigator, right? I wanted to do like a model just in Ecuador with all of the data in Ecuador to see how the how the geomagnetic field varied here. So in this sense, of course, I want to do that again with the compilation from my data and from the other data and most the data that I found. For example, data from Peru, from Colombia that they are not published, but they are, for example, in the database that I found, but a little bit, but some of the data that I published from Colombia, from Peru, that are close for this country, and trying to do at least a focus in Ecuador like a model. And of course, as you said before, yep, I when I was trying to figure out the tectonism on Ecuador, I could not said like a final conclusion on how this affect. I just see it could be affected because we have that, but of course I need to in the future, for example, in the for the publication, if I need to focus on that on the in the tectonism, according with the paleomagnetic data, of course, I need to read a lot, but now I need to read a lot about the teton, the how how the these fracture zones affect the Ecuador, how these the subduction are affecting Ecuador, how much degrees uh, are those those plates are subducting. Of course, I need to read a lot about tectonics. But when I remember that I was writing the thesis, I was more focused, for example, in the excursions. I was more focused, for example, in how to analyze the fork diagrams. So that is why I didn't focus on that on the in the interpretation of the structural geology. However, it's good and honestly really appreciate your comment because, for example, if I in the for example in the publication, if I will add something about the structural geology there, of course I will try to do a better job there. So I will try to here, of course, even in the introduction, I will add a lot also for for all of the tectonic changes here in Ecuador in the introduction, in order in for the conclusions that the people who read the thesis, because people who read the thesis, they if I didn't add the key importance in the introduction, they at the very end didn't will they will not understand, for example, what is the the Payaptanga fault, or where is that, or how much degrees those blocks are displaced, how many sorry, how many meters those those blocks are displaced, and something like that. And yeah, I really appreciate your comment. And of course, when I write, for example, for the paper one, if I add something about the structural geology, of course, I will add firstly at the very beginning something related with that. But of course, I will bring all of these things that I will learn in order to try to improve this tectonic part from my investigation.
Okay, thanks. And did you obtain unsatisfactory results that were not presented in your dissertation?
Yeah, no, I really, when I was trying to figure out how the code, how the this code, because it was mass programmation, so how this data help us to improve the models. So because I want to do a model here in Ecuador. However, when I was trying, I obtained many mistakes, many errors, and I said, no, I'm better. I will focus in the important things that are, for example, trying to get the paleosecular variation, try to get how this changing or why this changing. So when I was trying to programming that, I just trying 1 month, and honestly, I give up. But of course, it will be really good. But for example, here I just talk with I talk with teacher from the Sao Paulo with Daniel. So of course she could help me in order to get in order with my data in with the all data that I could compilate from Ecuador and from the concomitant countries. So of course she could help me for the future in the case that I want to finish that thing that I just started with my data, but honestly I didn't finish because I uh, I have many headache with that at that moment.
Okay. And I was curious to know why you didn't perform intensity measurements, because most of your samples have a magnetic mineralogy that is very promising to obtain good results.
Yeah,
But
I think honestly I think because of the time. because of the time. Because after that, when I was like trying to do everything, I I I it was a really nice story, honestly. So I was in Brazil. I just arrived here like 1 month and a half, and in that 1 month and a half, the process for the police department was open. So I was just applied there, just in case, because when I was chilled, all of this since I was chilled, my dream it was like a police officer. So say, and they asked for my profession for the first time in the old Ecuadorian history. So I said, probably could be," and I applied there, and there I just applied. I did all of the tests in that 1 month, and then I returned to Sao Paulo. Then I have to return for one thing from my mom, and when I return and when I was returning to Sao Paulo, received when I returned to Sao Paulo to get the paleointensity analysis. I I received the message that I already have the flight boat. So then I received that I am accepting for that, and when I know that that new I talked with Ricardo, I talked with Elisa that this I was accepting for that. So I already have all of these measurements did from all of the sites. So the next step for for my purpose is do paleointensity. But of course, paleointensity even could be better because in the future it could be even another publication or another study just for paleointensity, just with the paleointensity and with trying to contrast with my own data. And in the future just could be a paper that I read a lot of paper just with paleointensity with these results. So that is why when I was accepted that, I said I was reading some papers, and I read that in some senses, and I read that the paleomag, the paleosecular variation, that magnetic excursions, at least for now, because of the time and because it's like, well, principally because of the time, it was like enough for to present a master thesis. They are a lot of data, and even if I will in detail, as in the thesis, in some parts I was really in detail, so we could speak from the thesis like 3 hours, something like that.
Okay. Wow.
Yeah, it's a nice.
Yeah.
This is a general story. It's not like the deep.
Yeah. And now I would like to go into a specific point in your work, just one. Why was not made a comparison between samples that showed greater dispersion of AMS with the shape of anisotropy, like prolate, oblate? I mean, for example, in samples SE4 and SE17, figure 15.
Yeah, let's. I can share the. Let's see. Let's see. Yeah. Yep. Now I think. Let's see, where is the thesis? Nope. I think here. Yep. Here. Figure SE14.
15.
15, right?
Page 44, 5, I think. Oh.
Yeah, I'm not expertise in this area, just curious. So you wrote in your dissertation that the samples, for example, samples SE4 and SE17 is these samples present a great dispersion. Sorry. Yeah, but it's, I mean, I think it's not just, but I think it's a prolate shape right?
Yeah, SZ14 as SZ17.
Yeah, in the same figure. Yeah. Look at the SE4 first. SE4.
Yeah.
It's have a great dispersion or it's a prolate form.
Mm-hmm.
What do you think?
Yeah, I think at least for SE4, honestly, I think that this is, of course, as you can see here, and I honestly I didn't know why I didn't choose that, but of course, as SE4 belongs from here to Igualata volcano, and for the group 1 of the Igualata volcano, this group 1, almost all of the samples from this group fall in this region. So even with the stereo net and with this the shape parameter versus degree on anisotropy, yeah, I don't I don't I don't think that that data was like really important. But now that you said, of course, in the future works or something like that, I will try to correlate the shapes, and with these at least add the shapes, and of course these stereo
Stereograms, yeah. Because I think this type of correlation can provide an indication of the dynamics of the flow, lava flow. I just, it's my guess. I don't know in deeply. So, into my last question was the last question of Elisa, but I would like to suggest you two main papers, just a suggestion. One is Monchiato et al. 2020 to make some evaluation about AMS data and magnetic mineralogy. I think you can get some ideas there. And another one about the South Atlantic magnetic anomaly. You can try Egbers, it's right, from
sorry,
from
which
Liverpool.
one?
You can try to study about the South Atlantic anomaly. Use the Egbers et al. I don't know, 2020, 21. I can send to you. I think there have some nice ideas to use in your work. Just a guess again. And that's it. Thank you again. And yeah, I'm finished here.
Yeah, no, thank you so much for your comments. Honestly, I will applying almost all of your comments, and I will try to do that correlation in order to get the dynamics of the flow. Because at the beginning I was just focused because I read the paper from Mosinjato, and I just like trying to I like my vision it was like to the flow direction, because of I want to understand how this flow direction affect, for example, the tectonic, something like that at the beginning. And I didn't repair. No, I don't know how to say in English, but I didn't see like the other things from that paper. But of course, thank you so much, and it will be help me in order to improve at least that part of the thesis of in a publication when the time being correct.
So thank you very much, Wilbur, for all your comments and your thorough analysis of the thesis. It's interesting that after all the comments of Elisa, you could still pick some very interesting comments by yourself. It's a challenge. I think that there are things to be said, and then I think that the comments that you've made and the questions that you have made both help to understand more or less the context of the thesis, and that's something interesting to point out. Is that Kleber's one of our students that came into the pandemics, so he was one of our master students that went through the pandemics. And this was not easy because in the lab, being together with the other students and with other people is very important to do the work and to assimilate other knowledge from other people. So being alone or being during the pandemics in the lab was not as easy as in other times. So for that, I congratulate him for doing this work in this very hard time. Part of the work was supposed to be the paleo intensity as well. So the idea was to do paleo directions and paleo intensity. But as he said, there were other things in his life that moved him away from the magnetic world. And now he's doing other things. But I think that, and we thought and we discussed that the material he had on paleomagnetism and anisotropy was enough to build a master thesis, at least in the Brazilian model. So that's why we decided that it was okay for him to move on. So that's the main reason why we didn't explore the paleointensity. But the idea is to have all those samples and sites and check for the thermal stability, and then try to do paleointensity as well. So that's a step forward, and I think that you pointed out very nicely this, and Elisa as well, that what's next for sure is to explore better the relationship between the magnetic mineralogy and other anisotropy and paleomagnetism, but also paleointensity. That's an important thing to do. The paper by Opdyke, he has published some paleointensity results. They are not good at all. So I think we can do a good job in improving this part of the database that's even more scarce than the paleo directions. So I'll go only through 2 or 3 comments that you've made. The importance of this study is that we have very few results for the Southern Hemisphere and for the, that's clear. But not only that, there are also few full vector results everywhere, anywhere in the globe. So this is a very nice opportunity to have a full vector study. Having the directions is just the beginning. So we need the pilot test to do that, but that's something that needs to be done. And collecting the samples is a very strong step forward, because it's really not an easy. It's beautiful, like Kleber has shown, but it's really not an easy place to go and to collect samples. So that's something to be said. Elisa asked about the difference between the TK03 model and the model G. Those are 2 completely different ways to treat the geomagnetic field. One is using giant Gaussian processes, and the other one is just to taking the odd and non-odd components of the field, and then making a model using the global field. But both of them are axisymmetric. So that's what those 2 models do. And we say it's easy to see that the Kleber study and also the other study by the Opdyke, they just touch the 2 different models, which more or less coincide close to the equator. So there's something to better understand there. And then the compilation of all the results from Kleber and Opdyke be a way to go forward as well. So that's something to be considered for a paper to be published. Okay. I have something that Wilbur said, what Kleber taught at the beginning to do and what he did at the end. So it sounds to me like the Dunning-Kruger effect, you know, that at the beginning you think everything is possible, that you know everything, and then after some time, you just realize that, okay, maybe it's a bit more difficult than I thought. And at the end, you say, okay, maybe now I know how difficult it is, and then what are my limits. So this somehow shows that he has acquired some maturity throughout the process. And I think that's why I think that even though he didn't do everything he wanted to do, the thesis that was presented is enough to provide him, to give him a title of master. Those are my comments. I would like to comment also on Kleber himself. He is a very hard working guy. He's an amazing guy to work with. He's been a pleasure to have in the lab. We went to the field to work on other things, doing his master's as well. And he's also a pleasure to be in the field, very responsible. It was very nice to have you around, Kleber. So thank you for being here and for working in our group. I only wish you all the success in this new path that you have chosen in your career. Kleber, now we are going to close our judgment in a different room. So you can stay here. You're going to be, you're in the YouTube broadcast, so you can talk to the people. And then we are going to get back in some minutes, okay?
Okay, I will wait here trying to talk in YouTube then.
You can entertain the crowd.
Yeah, please don't out from this side, from this room. Okay, I will go to YouTube now.
Okay.
Bueno, para los que no hablamos ni inglés, ni portugués, ni nada de eso, ahora está deliberando el jurado. Entonces, de aquí a poco el jurado va a venir y va a decir, ya, y el jurado va a decir si el proyecto de disertación fue aprobado o no. Eso, para toda la torcida del YouTube. Y muchas gracias. Muchas gracias por su tiempito, por estar aquí. Y sé que, bueno, los de Ecuador tal vez no entendimos mucho, pero su presencia es bastante buena. E a gente do Brasil, que eu gosto muito. Também muito obrigado pela sua torcida. Eso. Y mi mente colapsaba entre el inglés, el español y el portugués, pero así bien creo que sí me fue. Esperemos del jurado, que eso es lo que ahorita están deliberando. Muchísimas gracias. Para que no se vayan, me pongo a bailar un poco. No, mentira. Eso. No, no voy a hacer nada porque esto queda grabado, entonces no, mejor no hago el ridículo. No, de nuevo, muchísimas gracias por su tiempo y por los comentarios, ¿no? Muchísimas gracias, Nine, o Gelson, o Giovanni, mi hermano Darío. Muchas gracias a Cristian, a Marina. Muchísimas gracias a Nelly, a Edwin, a Gelson de nuevo. E muchísimas gracias, Juliana. A gente foi com você para todo o Nordeste do Brasil. E na apresentação saiu a foto. É muito legal. Agora, hoje eu coloquei nessa foto na apresentação e falei, oh, Juliana. Aí eu lembrou que agora que você estava na Europa e agora no Brasil. Mas estou muito feliz também por Juliana, que agora está fazendo seu doutorado, né? Muito legal. Muchas gracias a mi esposa, a mi padre que siempre me acompaña, a mi tía Elena, muchísimas gracias, y a Nine que han escrito aquí, muchísimas gracias por su tiempo y por estar aquí. Y chuta, sí, no sé qué más hacer para entretenerles, así que ya llegue nomás. Espero que se demore unos 10, así minutitos que ya, para que ya vuelva, o 5.
Hi, Josh. We are back.
Eu estava aqui dançando com a gente. Estava tentando aí que a gente fique no YouTube, no podcast do YouTube.
Okay, so
assim.
yeah, I'm sure that people were much more entertaining in those minutes than in the whole thesis defense.
Yeah, I think so.
So now we are here to announce the decision of the jury. So after carefully analyzing your volume and all your work and also your defense, we all three anonymously consider that you're approved for your master, pending some corrections in the text that were identified by the reviewers. So you have you're going to have 1 month to do all those corrections. And you can talk in detail about that afterwards. But for the moment, the message is that you're approved and you're now a master of geophysics. Congratulations, and congratulations to all those that were around you and supporting you. If you want to give any final speech, the moment is for you. So just go ahead and speak.
No, first I want to say thank you. Firstly, the Elisa, that is the people who like said me about the paleomag board, and I think to she, I think I know many interesting things around the world, but also all of his comments, his suggestions, his time, and that he gave me at some point, and now even for this thesis, some comments from here were really important to improve even my firstly my life, but of course to improve all of the investigations in which we were working. So thank you so much, Elisa. As I said, always all of the good things that happens from that I started geology until now, I think, is because of you. And now again, thank you so much, Ricardo. I think sometimes you say like, Kleber again. No, es brincadeira só. No, mas eu agradeço muito, Ricardo, muito pela sua paciência, muito pelo seu tempo, muito por todos os trâmites que a gente precisou fazer lá, né? Que não foi nada fácil, a burocracia é igual que aqui no Equador. Então, as coisas que a gente precisou fazer, muito obrigado por dar-me sua confiança, sua amistade. Eu espero também tentar ter sua confiança. Muito obrigado. Os dois sabem que Elisa and Ricardo have here, like in Ecuador, like a family. When you want to come to visit the Ecuador, of course, you could visit, and I will hospedate at my little home now. So that is, no, I just want to say thank you for everything. Muito obrigado por todo. Agora minha cabeça não pensa muito bem, porque eu estou tentando falar três coisas, três linguagens, né? Mas isso, Wilbur, muito obrigado. Eu conheci você agora, mas eu agradeço pelo seu tempo que você deu para a apresentação, deu seus comentários bons aqui. Então, eu agradeço muito pelo seu tempo e agradeço muito pelos seus comentários e pela aprovação também. Então, isso, agradecer a mis padres, que de nuevo son también, ¿no?, el pilar fundamental para que todo esto para que todo esto suceda. Entonces, nada, só agradecimentos aqui e mais isso. Muitas desculpas se algum dia eu enchi seu saco, aí eu não lembro se essa é palavra ruim ou não, mas eu espero que aqui no Equador também tem um amigo onde vocês, qualquer coisa que a gente precise, eu estou aqui para vocês e isso. Muito obrigado.
Thanks a lot, Josh. You have a friend here in Brazil as well, so I think you have lots of friends. So you can also come whenever you want, okay?
Yeah, same for Iceland, if you want to come. A little bit colder environments.
Okay. So nice to have you all. See you, and then Elisa and Werbo, I will sign for you because it's something that was done online. But then I will send you an email for you to send me an email to confirm. In this way, it's official, the whole decision. Okay. Thank you all. See you.
Thank you so much.